Welcome to the presentation of our study entitled Sim2real Gap is non-monotonic with robot complexity for morphology in the loop flapping wing design, which is the result of a collaboration between the DST Group Australia, University of South Australia and the University of Vermont. Morphology of a robot design is important to its ability to achieve a stated goal, and therefore applying machine learning approaches that incorporate morphology into the design solution space can provide scope for significant advantage. Our study is set in a domain known to be reliant on morphology, flapping wing flight. In this video, we show visual demonstration of the observation from our experiment, that for a set of varying complexity flapping wing morphology designs, each of which are aiming to produce vertical lift, the resulting Sim2real transfer performance in terms of lift achieved compared to that predicted in simulation degrades with design complexity, and that the degradation is non-monotonic. The video shows three separate example wings flapping in simulation on the left and in reality on the right. The wings' complexity and Sim2real disparity are plotted in the center, which highlights the degrading relationship. In this paper, we consider a challenging problem space where the intuitive design approach to morphology is not available. Bio-inspired flapping wing flight, where construction materials, actuation, and the environmental forces being experienced by the robot are not within the realm of traditional design experience. Without a guiding intuition, manual design of a robot morphology can degrade into systematic forms of trial and error, and applying machine learning approaches to morphology design becomes appropriate. Inspired by the ability of natural evolution to produce a diverse and complex structure, evolutionary robotics has developed tools to facilitate morphological research to produce robots with novel morphologies that a human may not consider. Automated design of these robots in simulation for transfer to reality, Sim2real transfer, is challenged by the reality gap problem. The reality gap is the observed difference between the performance of a robot with high fitness in simulation and its real-world equivalent, and remains a critical issue for robotics. The ability to produce simulations that match reality for arbitrary behavior and morphology exceeds currently available physics simulation packages, and when we consider the effective material properties, non-homogeneous materials, stiffness, aerodynamics and friction, to name a few, it is easy to imagine a range of ways that robots designed in simulation can produce behaviors that will differ from those seen in reality. To begin to address these gaps, when morphology is not fixed, which we call morphology in the loop design, we seek an understanding of the shape of its reality gap. Our experimental workflow is shown here. Human designers often seek inspiration from biological examples that natural evolution has honed over the eons to achieve their spectacular capabilities. Rather than direct mimicry of the morphology of biological wings, we approach the challenge of morphological design by identifying the salient characteristics of the biological examples to use as building blocks in a machine learning approach that can automatically specify new morphological designs. This paper presents our Sim2real morphology in the loop design within our parameterized morphospace for the flapping wing aerodynamics problem. We have created an evolvable design specification, a genotype, that can be expressed to create a single structured flapping wing robot, a phenotype, for analysis in a simulation engine, or for the transfer to manufacturing and assessment in reality. Our flapping wing simulation decomposes a flapping wing design into a set of span-wise aligned connected flat blade elements. Each individual blade includes local geometry, span and chord length, values that collectively determine the shape, span and inertia distribution of the entire wing. The blades are sequentially connected by joints that allow elastic deformation in both chordwise and span-wise directions when the wing is under load. Within the simulation, all size and stiffness characteristics were quantized to match those available in the real wing fabrication. Each blade embodied a state-of-the-art quasi-static model for flapping wing aerodynamic forces and torques. The simulation was then encapsulated into a physics simulator shown here. The workflow visualizes the simulation of three different individuals and visualizes the instantaneous quasi-static normal and axial forces of aerodynamics as the red and green lines for each blade. To support Sim2real transfer, we developed a cost-effective manufacturing method that produces a wing that allows controlled variation of span, shape, elasticity, and inertia. These designs are automatically generated from the wing specification genotype into engineering drawings that are used as templates for the manufacture of the primary spar, chordwise elastic elements, and the skin. To assess real-world performance, a flapping wing test rig was developed. Our test rig drives the wing repeatedly through a single flapping axis using a linear solenoid actuator with magnetic plunges monitored by a position sensor. The actuator and wing assembly was mounted on a force-torque transducer such that the force generated by the actuated wing were recorded for lift analysis. We conducted automatic design using evolution by defining a genotype structure that could describe designs that spanned the entire morphospace. We placed the development of a population of these genotypes under evolutionary control and simulation, searching for designs that maximize lift produced while minimizing drive power and torque. In optimizing across more than one dimension, rather than determining a single best morphology, the search tool produces a set of individuals known as the non-dominated front. Within a non-dominated front, each individual represents a single design that is superior to all others in the population on at least one of the objectives. The front served as a rich set of varied design solutions to select from for transfer to evaluation in reality. For all the designs we transferred, we measured two quantities. The first was the complexity measure for the simulation robot, derived by the size and number of blade elements used in the simulation environment. The second is the Sim2real disparity, which is the difference in lift between the real and the simulation wings. Both of these variables are normalized by the maximum values seen in the design process. The key result from this study is the scatter plot shown, which is a plot of the Sim2real disparity against the complexity measure for a set of transferred wings shown by each of the black geometric points on this plot. The plot also shows a number of overlays that are important observations. First, overlaid on the plot is the regression-selected polynomial line of best fit for the transferred points, shown as a green dashed line. Also shown is the bounded region of upper and lower Sim2real disparities values observed across all the wings that we transferred, shown as the pink shaded area. The shape of the pink region and the line of best fit represent the empirically measured shape of the reality gap for the flapping wing design as we varied complexity. The second overlay of interest is the linear line, shown in red, which was fitted to the dataset and represents the monotonic decay that could be predicted from previous FEA analysis reports. It is pretty clear from inspection that the empirically measured shaded region and the polynomial line of best fit is substantially different to that prediction. The shape of the reality gap that we have measured identifies a non-linear relationship where Sim2real disparity is small up to a threshold value of complexity around about 0.6, after which the Sim2real disparity falls off at a much faster rate. The third overlay of interest in this example is that we identify a region of the plot where substantially improved performance was obtained in reality compared to that of simulation. This region is highlighted in blue and represents an area where the model is insufficient to capture a crucial positive operating effect. Investment in simulation improvements in this zone are likely to result in improved search results, and development of methods to automatically improve the modelling environment in this zone would extend the automatic design capability. This study has produced one of a few examples of morphological evolutionary search across the Sim2real gap. And for the first time in this study, we measured the shape of the Sim2real gap that emerges during morphology in the loop robotics design. The shape of the reality gap for morphology in the loop design observed in this study is the first such measurement reported, and it remains to be seen if this shape holds for other morphology domains. Future efforts to widen the type of robot and simulations are needed, as well as consideration for automatic ways to feed back details of areas where reality outperforms simulation to automatically improve the simulation predictions.